Um, so I guess today we'll start talking about algorithms.
Yeah, yeah. So, you see my screen here?
Yep.
Okay, cool. Um, so so we're in GraphBLAS, and I just released I think it's GraphBLAS 9.3.1 now. Yeah, 9.3.1. Okay, and so all the source files have been uh, restructured now, so it's easier to follow. In fact, all of our sessions have been with the draft 9.3, so these folders are there. So the algorithms, I think um, one interesting thing to look at in the structure here, you see a ton of these folders. I'm in the source folder right now here. If you look, for example, in the apply folder, this is GRB apply, which are very simple algorithms, probably the simplest. But there's some subtleties to those applies because some of them are indexed, unary, binary bind first, binary bind second, blah, blah, blah. Okay. There are there's all these folders have three kinds of they have source codes which go compiled directly into GraphBLAS itself. And then they have three subfolders: factory, include, and template. Factory are used only in the to construct the factory kernels. So they're template files, if you will, but they're not needed for the JIT. They're things like let's look at apply factory. For example, the unary op factory. Okay, it's just a massive switch case that is going to implement all of the built-in. It's going to call the factory kernels. So that's kind of boring. Just a big switch case for the built-ins. The include files are various definitions for that set of algorithms. And then the important, which are useful to see, but then the important part are the templates, which are the templatized kernels that are used in lots of different places. Typically, the JIT kernels, in particular, the factory kernels use them as well. And those host the parts of the algorithms that are data dependent on the data type. They're templatized. If there's algorithms that don't depend on the data, they only work on the integers, the structure, for example, then you typically won't see, there won't be JITted. They'll be in the primary source, which is here. So the source codes at the first level go directly into libgraphblas.so, and they're not templatized. And if we look at the pragmas here, you'll see a lot of where the parallel algorithms are. And they're all in the templates, in this case, for apply. So I don't think we want to see, well, I'll just look at these really quickly to see if there's anything interesting. I mean, the applies are super simple, except for this one. This is interesting. This is very trivial. So the applies are all trivial. Basically, just iterate all over. Here we go, like apply unary op. Boom. It's like, how simple can this be? It's only this is a little snippet of code that's included into other code. It's templatized, so it can be with these macros. I guess it's the X macro idea. So it's applying the operator, and usually I'll precede the operator or the thing I'm doing with a more readable version of that. In this case, apply an operator and store the result in the numerical values of the output array. And this is a super trivial algorithm, right? Just iterate all over all the entries, skip if it's bitmap and the bitmap says no, it's not there, and then do the work. Okay, so that's as simplest algorithm as you can get. But this one's more interesting, and I think I'll start here because it illustrates some of the constructs I have to use to parallelize an algorithm for a sparse matrix. So this is applying a unary operator that depends on the column index. Now remember that when you're looking internally at the code, the code is written as if all the matrices are stored by column. They're not, of course. They can be stored by column or by row. And all these kernels are agnostic to this. If I have a CSR matrix and I call this code, well, then the I's and J's are reversed. I mean, it's the same kernel, because my matrix is just a collection of vectors. Each vector has, entries, and then I have a flag that says, oh, do they go by row? Do they go by column? And then so once I decide at the highest level what matrix am I working on? Is it stored? Is it four formats: hypersparse, sparse, bitmap, and full? And is it stored by row? Is it stored by column? And is it transposed? And does the descriptor say to transpose it? Because a CSR matrix that's transposed is identical to operating on a CSC matrix, and vice versa. So I merge those together into just the two cases instead of four. And so here is the guts of an algorithm you're seeing after I've done all of the parallel thread construction. So I think actually it would be useful to look at apply because it's so simple. And let's look for where I use this particular kernel. It's in the apply op. Okay. So let me go to matrix apply. So you call GRB apply. That's obviously a GRB apply. Actually, let's start at the generics. GRB apply. GRB apply is not a method, right? It's a macro. And it's the ugliest macro you could ever imagine. Actually, this is the worst case. This is the worst case for my generic kernels that are the polymorphic, because the spec calls upon the spec creates something like 87 or 89 different instances of GRB apply. That's the spec. And then I add some more because of complex types and such. It's absurd. Because you can apply with a C scalar, you can apply with you have to have these type, int32, FP32, and so forth. There's 13 of those, and there's 13 of these, and there's 13 of these, and there's 13 of these, and it just goes on and on. Okay. So I fold all those GRB applies into one method, and then at the very end of the day. So let's start then. So you call GRB apply the polymorphic, and it's going to call, say, this method, or it's going to call one of these many specialized cases. And these are all going to, let's see, at the end, eventually they'll all call the workhorse method GB apply, which is my internal method that's doing the work of apply. So, if it's a scalar, I'll wrap it in a C scalar, I'll wrap it in a GRB scalar, and so on. So GB apply is doing the full work, but I come in initially to the user callable code, and I'll go a little bit more detailed in some of this structure because all the other algorithms are going to look the same. The first thing I have to do is establish where I am, GB where, because if an error occurs, I have to log the error in what? Inside the C matrix. That's where an error, like you say GRB error, you call GRB error on the matrix C, you get back a string that says, here's the last error for this matrix. So I have to keep track of for the logging, where I am and who's got which matrix has the log string. That's what GB where does. It's just a macro that everything starts with. And it also, GB where also starts up you don't see it declared here, but I have this little strangely misspelled thing called werk, W-E-R-K, and that's actually declared here. It's just that space is a statically declared array of bytes that just gets stuck on the stack. And it's used for, if I could reliably call, I think it's called alloca in C, alloc, right? Allocate space on the stack. I would just use that because then we return, it's gone, and it's good for small things. But I don't trust it. And Windows is notoriously bad on stack management, so I just do it myself. I use this little array for small things that otherwise would have to, like, I need, if I have 40 threads, I need an array of size 40 because I want to define, or maybe not 40, maybe maybe 4 times that. Because if I have 40 threads, I might create, say, 10 tasks per thread. I might have an array of 400 tasks. Well, 400, that's it. 400 integers, that's pretty tiny. Stick it in this Verc space. So that's where that kind of thing goes. And if that space, if that stack is full, I do malloc to the space. So that's what GBWare does. I start with that. And then I've got my burbles. And so this starts the burble, do my error checks on the input matrices, and extract information from the descriptor. This is also a macro that calls a function and then declares these contents and then extracts those things from the descriptor. And then get mask. Let's see, why don't I go to that first? So get mask.h. I guess it's a static inline. Okay, so get mask constructs a new matrix M, which is either the input matrix or none at all. Okay, no mask, because I might decide to throw the mask away. So it's not actually, it's a const, it's either the user's input matrix or it's null. That's what this mask is. So what I do here is I've gotten the descriptor and I have a mask matrix, and the mask could be complemented or not, and it could be structural or not. I'm going to change this because if the mask, there's a case here where I want to capture and simplify for all methods, and I do that with this get mask method. If the mask is present and ISO valued, but it's not structural, well, hey, I can make it, maybe I can just make it structural. I will make it structural, in fact, right now. And if it's not user defined, you can't have an ISO value. In fact, this was a discussion actually at the GraphBLAS meeting, is how do you cast a Boolean from a user defined type? There is no such in GraphBLAS. It's not built in. So if you have an ISO valued user defined type of a mask matrix, and you ask me to use it, well, I'm just going to error out at this point because you can't use it. You can't use, I'll return an error at some point. But in other words, you can't do it with user defined types. So you have an ISO valued mask, a mask matrix that's treated as a valued mask, but it's ISO valued. Oh, well, then I can just check the thing if the thing is non-zero or not, that ISO value. If it's non-zero, well, then it's a structural mask. It's always a structural mask, and you have a mask matrix, and here's your structure. So I just convert the thing, a valued ISO, a mask that's ISO valued, that's treated as a valued mask, is turned into a structural mask if the value is non-zero. If the value is 0, well, then you have no mask at all. The mask is false. So it's a let's see. It's the same thing as a mask with no entries at all. And mask complement has to be negated for this to work properly. for this logic, because a mask that's not present is as if all entries are true. And so I have to negate the sense of the complement of the mask. And then I say you have no mask. I throw it away. And the logic works, right? If you work the way the mask works, this is just doing some very quick handling of the mask, and I just simply throw the mask away entirely. Okay, so that's the mask, and then I call the computational workhorse. In this case, it's GBApply, and pretty much every GRB method or GXB method, user callable method, has this workflow. Like if you look at, say, MXM, GRB, MXM, it's the same kind of workflow. I log where I am, I start the burble, I check my input matrices to see if they're null or uninitialized. Null or faulty is what that means. I grab the descriptor, I grab the mask, and I call the workhorse, the internal method that does all the work. And for that, because GBMXM is going to be called in 3 places. It's MXV, VXM, and MXM all call that method. The same thing for apply. I bring all these together into a single method, and so let's, whoops. Okay, so let's look at apply. So now I'm calling GBApply. This is, now we get into the guts of the algorithms. And so I've got the output matrix, and I've got now all the descriptor has been burst apart into its components. I no longer use the descriptor. I've thrown it away. Well, obviously it's the user's descriptor. I don't delete it, but I don't pass it to my internal methods. I don't need it. I just pass in the pieces like, is A transposed or not? Is the mask here's the mask. Is it complement or not? See replace, and so forth. All the things I need are passed to the methods. And in this case, and it's indented in a funny way here in this, because the operator is described with these 3 things. And I used to have just a GRB unary op, and now it's burst into 3 things. I have a single type, I have a single object internal type called GB operator, which is any operator of any kind. And then I can just quit, because all my operators have the same data structure. There's just a flag inside them, like an enum code that tells you which operator it is. So I can tell, oh, you're unary, oh, you're binary, you're index unary, and so on. They all have the same struct. So I cast this. In this case, it's a GRB unary op that gets cast to an operator, which has no scalar. There's no GRB scalar for this. And you're not doing a bind first. It's otherwise bind first is false. It'd be bind second, but it's a unary op, so I'm not going to use that at all. Okay, so now I'm going to start to do the next phase is the sanity checks. And I'll often start with, so I checked the sanities for the the inputs, like more of the inputs, which I've checked already in the caller. I also have in my code lots of assertions. Anytime you see the word assert, you know it's not a runtime check. I'm sorry, it's not a production time check. It's only for development. If you want to enable the assertions, and this is very useful for debugging, so it's very useful for me to describe this. I'm asserting here, hey, this matrix is okay. Now that's turned off. If I want to turn it on, I can go to the, I think it's called gbdebug.h. I forget what it's called. Or I can just do this, define gbdebug. If I do that and recompile the code, then all these assertions become active. And
what is an okay matrix? Is it like some sanity checks on it?
It's a complete sanity check of the matrix. It walks across the whole matrix. It's the same as my print code. It looks at the entire. Oh yeah. So let me show you what that looks like. And then this flag GB0 means don't print anything. So it's terribly slow. I don't care. And And if you want to, if you have some bug occur in this method, you can turn on debug and you can set that GB0. What I do here is I say, oh, just do a global replace of the GB zeros to GB5 or something like that. And that'll print all the matrices as you're walking through the problem. And the matrix OK, I think I defined this in OK. Yeah, there we go. Include assert kernels. Oh no. Okay, this is what happens inside the JIT matrix. OK, just becomes an empty. Yeah. Once you're inside the JIT, I disable debugging. When if you JITted a kernel, it's too complicated to allow the JIT to call these assertions. So, but gbassert.h matrix OK does the following. It asserts that it calls matrix OK. It assert matrix OK calls GB matrix check. And I think that's in the print. GB matrix check. Yeah, it's right here. This is the thing that prints and checks a matrix. When you do GRB print or GXB print, say, it calls the same method. That method both prints and checks a matrix. It's very slow, but I don't care. If I go look for print GB matvec check, whoops. I guess is it check? No, print GB matvec check. Here we go. Okay, this is 1,000 lines of code. This is a very useful piece of code. It validates exhaustively a matrix or a vector, because a vector is just an n/1 matrix. So, and I print out. I mean, if it has a single column, say, then it must be a vector. But I pass in a string so I can, when I print, oh, you have a GRB what? Oh, you have a GRB vector. So I don't confuse the caller to say, wait, I printed a vector. Do you say it's a matrix? No, I don't do that. So this thing walks through the matrix and it goes through. And so this is a very useful companion to the GraphBLAS, my GraphBLAS GRB matrix itself. This is the sanity check of that object. And as it's doing the sanity check, it's also printing the thing optionally. And so it checks it checks to make sure, it gets the contents of the initial content, the header, from the header, and I decide what to print. I print out what type of matrix the thing is. I print the name of the type, like, hey, you've got this matrix. It's 4 by 10. It's float. And it's a matrix, and it might be a phantom matrix. That's another internal thing. Then only for internal not matrices. I forget what a phantom matrix is. It may be a null. It's like you print a matrix. Let's say a mass matrix. It's null. It'll just say it's null. Make sure the magic is correct. The magic is a 64-bit integer that says if it's been initialized or null or freed or valid. The type of the matrix and what the sparsity control is. And I'll print out, I'll do a sanity check on the validity of the contents of the vector structure. Like if it's sparse, for instance, these properties have to hold. I count up how much memory I'm using for the matrix. That's this right here. I call this method called memory usage. It tells me how much memory does this matrix take. I validate the check, the type. So this is what, if you want to print a type, it's called the GB type check method. So, oh, it's int 32 or it's a user defined type. And then I go through and print, I do sanity checks on the structure. I walk through, check the pointers, check the hypersparse list to make sure, all these things must be true, like the P array. The AP of 0 must be 0. It must be monotonically non-decreasing. And the last entry must be smaller than NZ max, which is the size of the I and the X arrays. Things like that. All this sanity checks. Because if I've mangled the matrix somehow, well, then like if one of these things, if this fails, obviously, if I have a bug, if I have an input matrix that's corrupted, the bug's not here. The bug is somewhere else. So it's a sanity check of all my inputs, basically. And this is also what I call when I print the matrix too. So if I have a bug, I'll turn on debugging for this method. I'll enable GB debug. Debugging requires a text edit of my code to enable. And I do that on purpose because I don't want to accidentally have, ANSI C has this -d end debug. It's kind of like that, but I do it myself. And I do it such that you have to edit the code to turn it on because I don't want to make it easy for, say, CMake, set a flag, set on debugging. Well, now it'd be absurdly slow. I don't want that to happen by accident. So you have to turn on GB end debug. Let's see, GB debug, I guess it's called. This is the flag. And here I have a top level include file, which are kind of like stuff I didn't know where else to put. I include folder. I think don't have a top level template folder, do I? No, top level. And these are very high level. These are like system GraphBLAS wide sort of things, like GB dev. Oh, I don't use this anymore. Oh, actually I do. Here we go. Like if I wanted to turn, yeah, I do use this. These are code development settings that nobody uses except me. And if I say want to turn on debugging for all of GraphBLAS, I uncomment that line. If I want to turn on a kind of like I have my own Valgrind, okay, I turn on my memdump, and then I think there's other debugs I have for memory. I have another setting in which I can turn on. I think it's elsewhere, where I have my own table of all the mallocs I've ever mallocked, and I delete the ones I free. So it's the list of all live malloc spaces with their sizes. And it's a really stupid list. It's an order n time to search through. It's just for development, just for debugging. And then if I have a memory leak, I can catch it quickly, easier than Valgrind. And I can do things like when I free a space, the Valgrind won't do the following. When I free a space, my free method says, I'm freeing this space of 10 bytes. Which, why am I telling you how many bytes? Because, well, I want to know. I want to keep track of my memory usage. And I want to know, I want to assert then, is this thing really of 10 bytes? Well, I look it up in the table when I free it. And then if that table says it's 12 bytes, then I abort. I say, nope, something's wrong. But only do that in debugging. So I can turn on other development settings here. And then in the OK folder is where I have all my various assertions. This is just all these tons and tons and tons of assertion macros that assert objects are okay, assert something is okay, do various assertions, assert that, I guess okay, I forget what the difference is between, let's look at that, I forget what they are. Assert, oh no, that's not there. Assert, so assert okay, assert something, yeah, asserts a success. GRB success. Okay or null says the result could be success or null pointer. And that's true down here. Like you can pass in an accum that's null. So I assert that this operator is either okay or it's a null pointer. In which case I'm not going to use it because you didn't give me an accum. You passed in null for the accum. The same thing can happen for the mask. The mask could be null. So here, matrix okay or null. If you pass in a mask that's null, that's fine because I don't need one. So that's some of my debug methods and how they're useful. Okay. Now I've got to go and decode what the heck is I've just been given. I could be given any one of three kinds of opcodes, three kinds of operators: unary, binary, and index unary. And the operator could be positional. It could be an indexed. Positional means indexed. Same thing. It could depend on the indices. And some of my unary ops depend on indices. Some of my binary ops depend on indices because they're the ones that are like GXB first I. It's a binary op. It's not a GRB index binary op. It's a built-in unary or binary operator that does in fact depend on the indices, even though the spec says it shouldn't. But I kind of snuck it in there.
Well, it predates. They predate the index operators, right?
Exactly. Yeah. Exactly. I wouldn't have had to do that if I had them to begin with. I would have done this, but so some of the opcodes are positional. Okay, and now all these second level algorithms like GB MXM, GB apply. Okay, the first thing you have to do is validate. They have to continue validating the inputs, and the validation here does things like, well, is the type, are the types position, are the types let's see. Are the types compatible? Can you typecast? And if not, you get a domain mismatch error. And the positional operators don't have to check the types, like the ones that are built in. It's binary op, the same thing. I look at the not sure the logic here, but anyway, I look at the op is positional, but isn't first. Oh, first and second are not positional. It's first I and second I. Never mind. Yeah, this. So I also do things like, oh, you're calling with the second. You're doing a GRB apply with second, which maybe you want to do. You maybe want to replace. Maybe it's bind second. And the operator is second. And so you just want to take apply and change every value in this matrix to 3, except those that maybe fit in the mask, say. Okay, so if basically what I need to do is make sure that though you've passed in a scalar, it's a bind first or bind second. Here, let's see, because you've passed in a binary op. I have to check to make sure the domains match for the scalar you've passed in. Can I typecast from that scalar to the operator? And index unary op, same thing. I'm going to make sure, hey, there's a thunk. I should call it theta maybe. There's a scalar passed in. Is it compatible with the operator? Is the matrix compatible? I'd have to check that as well. Where do I check that? Yeah, I check that here. Like you're trying to pass in here, for instance, like if you're trying to pass in a matrix to say the operator, say the operator is square root. No, that's a bad example. Say the operator is, I don't know, yeah, like square root, and you pass in a user defined type. Whoops, I can't typecast. These types aren't compatible. A type is the type of the A matrix, and op X type is the type of the X input to that operator, whether it be a, well, in this case, it's a unary operator. It has the one input. So what you'll see in every method here, you'll see these things that log these errors or return an error. And in this case, I have to call this GB error macro because I've got to log the error string, and here's the error string. The error strings in GraphBLAS are really a pain in the neck to implement, honestly. I don't know if they do any good. Do people actually use those? I don't know. Maybe
Well, I
they're
know
useful.
we raised them as exceptions from Python, and you see the
Yeah,
message
you
in the
see them,
exception.
right? You see the
Yeah.
message. They're
Python's very
limited,
interactive, so a
right?
human eyeball tends to see it versus like a log. Yeah.
Okay. They're they're a little bit limiting, honestly, because the spec committee decided to put the error string into the output object itself. Okay, but what if the error is so bad the output object, say, is null, or it's broken in some ways, or whatever? There's no other place to put the error. So I can't log the error there. It doesn't, you lose the error string. Other methods, if they have an error, like GRB build, like a constructor, that's not a good example. There are places where I simply have no way of logging the string. There's lots of methods like that have no place to log the error. And so I just have to return the code, and that's it. Return the GRB info, and that's all I can do. So lots and lots of, like, for example, you've got C and A or C and A have the same dimensions. The dimensions have to match. Or if it's C equals op of A transpose, then I have to reverse according to the transpose. Does the C and A transpose have the same dimensions? If not, the dimensions are not compatible, and this is the string you get. So I have to check type compatibility, dimension compatibility, and so forth. And here I check the compatibility of the whole mask accum process with the types. Where is that? It's just, here we go. It's this method. I have a folder called compatible. Are these compatible? Here's compatible. This is the algorithm here. Okay, this is it. So there's a lot of error checks that are hidden inside this method. It's used a lot of places. If you have an accumulator, okay, then the accumulator has to be compatible. I have to check basically, can I pass C equals F of CT basically through the accumulator? And so I have a method called GV binary op compatible that checks to see, hey, you have an operator, you have some types. Can you pass that through the operator or not with those types? And if you can, great. If not, return GRB domain, mismatch. And here I check the and log the error. This also logs the error accordingly. Here I check the types. Like if you have C and T, the temporary matrix is a result of the result of the method. You all the GraphBLAS operations are described in the following. They construct some matrix T, and then they push that T matrix through the mask accum phase. C equals M of accum C comma T. The mask might not be present, the accum might not be present. I might not compute it that way. I might just do it all in one step, but mathematically, the types have to all work. And so the T type here, in this case, the type of the temporary matrix is for the GRB apply is the Z type of the operator. So I grab that and check it. So basically what you're seeing at the very beginning of all these second tier algorithms, all of them is this sequence of error checks. Finally, I check to see, oh, the quick mask thing. If you have a mask that's empty and it's complemented, then nothing happens at all. Almost nothing happens. C replace might decide, if it's true, delete the C matrix. And the result doesn't depend on the T matrix at all. So I don't compute it. I return right then and there. There's really no reason to do anything more. I just delete the matrix, empty the matrix of all its entries, or I leave it alone, do nothing. If you pass me a null mask that's complemented, nothing happens almost, unless C replace is true, in which case everything in the matrix is deleted. So return if quick mask happens in a lot of places. Okay, so now we start to get into specific algorithmic issues. There's usually then a wait phase where I have to check to see what do I need to wait for? What does this algorithm tolerate? Okay, this is an algorithm GRB apply. The apply methods don't care if the matrix is jumbled, which means if it's a CSR matrix, are the column entities out of order or not? If they are out of order, that's an unfinished matrix. But maybe I can work on it anyway. I don't have to finish it. So this matrix wait will occur if the input matrix has any pending entries or if it has zombies. If so, I wait, which means I finish the work. I sum up the pending tuples, I assemble them, I kill all the zombies, I sort it if need be, it's no longer jumbled, I finish everything on the matrix if it's got pending or zombies, but it won't if it's just jumbled. I'll just let it go, and because the algorithm's agnostic, it doesn't care if the indices are out of order or not. If I did depend on that, I would just call GRB matrix wait. I just wait on the input matrix. If I can't tolerate any pending work, I call just GRB matrix wait. And another final error check here, and I have to put this error check after the wait on the scalar, because I'm going to now check to see because with GRB bind first or bind second, or the index unary op, you pass in a scalar. That scalar cannot be it can be a GRB scalar or it can be a C scalar. Right now it's just now it's a GRB scalar because I've wrapped what I do at the you didn't see this, but at the very top level in GRB apply, if you pass in me a C scalar, the first thing I do, I say, ooh, I don't, that's evil. I wrap it into a shallow GRB scalar, which refers to, it's a pointer. It still refers to the C scalar that I'm using, but I have a whole scalar structure around it with a type and everything. So I don't have to have, I mean, otherwise, how do I keep track of the type and so forth? But I may wait on the scalar, which is nonsense because there's nothing to do. It's just a plain C scalar. It's finished, but I want to make sure it's got an entry. Because if you pass in a GRB scalar that's sparse, it's no entry, that's a valid GRB scalar, which is a really useful thing. Anyway, but you can't pass in such a scalar to apply. It's not allowed for in the spec. For a binary op or an index unary op that relies on a scalar, that func scalar must be non-empty. Okay, even though you might not use it. The next thing I do is I may simplify the operator, and I may decide to change it. So the operator, let's see, where is it changing? Oh, yeah, it starts out as the input operator, but I may decide to rebrand it. And I pass in the address of that. Let's see. If I rebrand it, I'll give it a built-in, so I don't care anymore if I overwrite the input not an overwriting input operator. I think it's going to be in bin up rename. Here we go. So this is a very simple table in which I simplify some of the operators down. So for example, if you pass in a binary operator and it's Boolean, I'll rename all kinds of Boolean operators down because there's a lot of really strange Boolean operators in the spec. Like there's a Boolean divide. Right? There's all kinds of weird Boolean operators. Really, trust me, they're there. I don't know why they put them. So I prune them down. I say, you don't want that. You just give me I have a whole smaller set of actual useful operators, and they map to those. And I also remap some of these. So for instance, if this is a case where if you pass first and it's not bind first, it just means that you are, let's see, it's bind second. Yeah, first bind second. Wait a minute. It's first and not bind up means bind second. So you're just passing in, you want everything to be this, great, the scalar. Hang on. The operator just becomes identity. Wait, the logic here is the comments are backwards. Hang on. This works. I'm just trying to remember what it's. Wait a minute. If the operator is second and it's bind first. Oh, yes, of course. Okay. Yeah, bind first is where the scalar goes. So you're either calling, yeah, this works. So say you call GRB apply with the operator second, GRB second, you pass in a scalar and you pass in a matrix and you say bind second. Well, oh, that's just identity. So just replace the operator with identity. And the pair operator gets renamed. It becomes a unary operator. The unary one. So there's, if you pass in the binary one, you get the unary one. If you pass in an index binary op, then I'll do things like I'll simplify the valued binary operators, like value not equal to GRB value NE is a index unary op, but it's the same thing as the not equal to binary operator, but with bind first, with the bind first being, let's see, false, I guess. So I replace the index unary op with the binary op, and you get the same result. So why have both code branches? I peel away some of the duplications here in these operators, basically. And so I get some simplifications of that. I don't have to consider all possible cases down below, because there's some are absolutely identical. And that's what GB binop rename is doing. And it's used in lots of places where binop rename, I guess it's used, well, there you go. It's only used in apply. Oh, well, never mind. I thought it was used in more places than that. So I've renamed the operator. So I don't have so many cases to consider, because apply is surprisingly complicated with all the different cases. The next thing I'll do is, and this is typical of all of these algorithms, I handle the I'll handle the transpose, I'll handle the I'll have a phase of my code where I will say, oh, you have a matrix stored by column, and the result matrix is maybe stored by row. So if they're different, then I'm going to have to transpose the matrix to get things to work, which means I have to change the descriptor. And then I'll say, well, if you have a matrix stored by row and you have a positional op, then I have to flip the operator. All the i's become j's and j's become I, because internally, agnostically, all my code is as if everything's stored by column. I only have one case, not both cases. Why have both cases? I just change the operators as needed. And so that's what these flip methods do. I flip the operator. And in some cases, if it's user defined, well, user defined, this would not be true. So some of these operators aren't going to get flipped. The user, if it's user defined, I've replaced all the built-in operators with their flipped variants if need be. But user operators, I can't do that with. I can't, because I don't have the flip variant of only of the user defined operator once. So I have to keep track of the fact that, oh, I have to, when I call the user defined operator, I have to flip IJ. In the code, unfortunately, I use the word flip for two different senses, and I really should fix this. I use this word flip for this reversal of I and J to J and I. Okay. I use it there. I use it in a similar sense, which it was probably fine, where I also flip X and Y of an operator. So if I do A times B and I decide to write that as B transpose times A transpose, well, the multiplicative operator has to go crisscross, has to flip. The arguments have to reverse. If the operator is commutative, like if it's times, I say, oh, forget it, I'll just leave it. It doesn't matter. I set that to false. I don't care, and I just call it as is. It just works. 2 times 3 is 3 times 2. It works. But if it's user defined, well, or if it's a divide operator, oh, I can't. I have to actually do the flip. I have to replace divide with reverse division, in fact, or a minus. I have a reverse minus method. Methods. So the GraphBLAS binary operators that are built in, many of them have, not all, many of them have like less than becomes greater than becomes less than. So less than is not commutative. A less than B is not the same thing as B less than A. And neither is greater than. But less than and greater than are a nice pair of operators because they're the reverse of the other. And so if I need to flip the less than operator, I just use the greater than operator instead. Every built-in GraphBLAS operator has a flipped pair operator. And if it didn't, I put one in, like divide. I have reverse divide for that reason. So I just take the opposite operator. But user-defined operators, I can't do this with. And so I have to keep track of that fact that, oh, when I call this user-defined operator, I have to go like this with the i's and j's, or like this with the x's and y's. In this case, I don't have to flip x, y. I think I call it flip x, whoops. Here, you're not going to see it because it's unary. But I think what I do for that case, act flip x, y. Yeah, see, if you ever see flip x, y, that means x, y have to be reversed in order. And that happens all over the place in GraphBLAS. Flip ij happens all over the place in GraphBLAS. Here, this is where it happens. It happens in the apply, in the transpose, in some of the JIT wrappers. It happens in select. It happens in the enumifies and codifies. I have to keep track of, is the thing flipped? And the same thing with x, y. I have to like do it to a lot of places, like the matrix multiply I just described. I think is the only place it happens actually. Oh, maybe it happens where else? Oh, I guess that's it. Oh, EY's multiply. I guess it happens there. Not EY's add. That's interesting. Why is that? Hmm. I'll have to think about that. So I have a flip XY, flip IJ, and it's the same thing. It's like those are the same ideas. They're reversing the order in the parameters that I when I call this operator. Unfortunately, I think it's in the folder zombie. Let's see, where do where is it? There we go. My zombie math. Okay. This is all the math operators. They're not really math. They're operators on a zombie. Zombie is an entry that's flagged as dead. And unfortunately, I use the word flip there as well. And it's a different sense of the word. It's a function that it's its own inverse. So GB flip is this function here. It's a negation about -1, if you will. Flip of -1 is -1. Flip of 0 is -2. Flip of -2 is 0. The function is its own inverse. It's like negative. It's like take 3 and you get -3. But that doesn't work because I want to negate 0, and there's no -0. If there was a -0, that would just use negation. And I use this to tag a zombie. I negate its index. So a 3 becomes, well, not a -3. A 3 becomes a -4, I guess. Or maybe -5, maybe. Yeah, a -5. A -5 becomes a 3. Because a 0 becomes a -2. A -2 becomes a 0. And then a 1 becomes a -3. A -3 becomes a 1. So I can kill it and bring it back to life again. And unfortunately, I used the word capital flip for that. So capital flip is not the same thing. And I probably should rename that. So I have a thing called flip XY, but I also have a thing just flip, which means flip a zombie. So this is a flip in the reversal sense, but this is a flip in the sense of a zombie, which is a totally different concept. Unflip means don't make it a zombie anymore. Take the absolute value, if you will. It's a unary operator, not a swap of two values. It's a unary, so it's very different. And I really should not call it flip. I should call it something else, like the zombie function or something. I just don't have a good name for it yet. But that's the zombie math. is are you a zombie, which is the same thing as this. Is flipped is the same as zombie. Maybe I should call it the zombie function. I don't know, because that's all I use it for. And unflip means if you're a zombie, you're alive, and if you're alive, you're still alive. It's like the absolute value. Um, so I should call it zombify or something crazy like that, so it's easier to grep for, and you don't get confused when you're looking at these two notions. See, this is not a swap of two entries, but this is a swap of two parameters. Um, so, oof. So that's its notion of flipping here is not zombies, it's reversal. Okay. Now this is okay. So now finally I'm ready to do the actual work. And I really should comment this differently. I should really do the following. I should put a thing here that says, oh, I guess I have it up above. Okay, never mind. So I I compute the I apply the operator to the matrix, and the result if is a matrix T whose type is the Z type of the output type of the operator. There might be a final typecast at the end to the output matrix, in which case I do that as another operation, which I really should fuse that. I could do that in the JIT. If you say a C matrix is double and you say apply the float square root to an int matrix, let's say, I should be able to do that in a single pass. I don't yet. I do that in two passes. I'll construct a temporary matrix that is, say, floats square root of the integer, and then I'll get a float matrix and the output is double, say. There's a final typecast at the end. The T matrix is that intermediate type. And I did this because I put this code structure in before the JIT existed. But I could fuse that and do it in a single step via the JIT, because the C and the T type would differ, and I would just typecast at the very end. That's fine. I just have a couple extra typecastings in there. But it's not pushed down yet because the logic didn't support that yet. So, but anyway, there's now 3 different ways of doing this apply. I may be doing a transpose, in which case the entire work is done in GB transpose, because I knew this was an important phase and to fuse. You may be doing C equals F of A transpose. Okay, that's a transpose and the apply of an operator at the same time. That's one kernel, that's one pass. That's the transpose method, which is no longer here. This is now going into the transpose code, which is much more complex. Transpose is 1,500 lines of code. Apply is going to be probably a lot shorter. Ooh, no, it's bigger. That's funny. Okay, well, okay, but the algorithm, the templates are more complex. In the internal algorithms of apply are very simple. The internal algorithms for transpose are much more complex. Yeah, well, not a lot more complex, I guess. Okay, so the transpose. The transpose method is a very powerful method. It's called by GRB transpose, for instance. You just there is a GRB transpose. Nobody uses it. They always use it with the descriptor, and it does the same thing. Like apply identity with a descriptor is the same as a transpose. But there's a transpose. People sometimes use it. And this is what this does. So for example, if we're in the transpose method and we call GRB matrix transpose, let's say, or just GRB transpose, I guess you can't transpose a vector. I literally just call GRB transpose. I guess transpose and cast. It does both a cast and a transpose. Anyway, so it eventually calls this method. Okay. So this transpose does the entire work of the apply, because then it has to be passed in the operator, and it does the transpose and the apply at the same time. So let's not dig into this algorithm. Oh, that's funny. IJ flip IJ. That should be flip IJ, not IJ flip. Anyway, otherwise, I have a let's see, where is it? I'll often have a kind of greased lightning path where matrix multiply looks like this. I'll have special kernels that require special cases. So here's a special case. You're doing an operator on the matrix itself. C equals f of C. Ah, that's really nice to know. With no mask, with no accumulator, C and A are alias to each other. And, well, no typecasting. Because if there's typecasting, well, that's weird. I got more work to do and it'd be more complicated. So I don't handle that case. In this case, I call the apply method directly, and I don't make a copy of the data. I work on the data in place. So this is going to take the matrix C, and it's going to write its result directly back into the matrix C. This is the output value. So GB apply op applies an operator to an array, to a matrix, to get an array of data. And so it's a very low level method, and all it does in a few places. It's in MXM as well, and in transpose. And apply op is very simple. It's now not writing its output to an array, to a matrix, but just to an array. And this is the workhorse of the apply. There's a lot of different cases I'll have to walk through. Otherwise, I have to create a matrix. But I don't want to just create any old matrix. I want to create a very simple matrix. So I have to create an output matrix T. It's different from the A matrix. But because I'm going to pass this matrix on down to the mask accum phase. So I'll often have this kind of bifurcation into special cases where I can do some grease lightning kind of cases, or the more general case. So this is the more general case, where I have to construct an entire output matrix and then use it later to finish the work. Here, I'm calling the lower level method directly on the values of the matrix itself. It works in place. This shallow op matrix is going to call this method, but it'll first construct a matrix in which to put its results into, and it'll be out of place method. T and A will have different numerical values. But the method is called shallow op. The reason this method is called shallow op is because this is, and so let's look at shallow op. This is a higher level method than the apply op. Shallow op is going to construct a new matrix C, but it's going to be a shallow matrix. And the operator is just applied to the values of the inputs to get to the outputs. However, the output matrix is going to be shallow. Most of it's going to be shallow. It's going to make a matrix here, like where most of the stuff, like the C array, this P array, the output matrix is now called C. Not, I'm calling it with T over here on the right. So this is a new matrix I'm building, but like C equals F of A, that C and the A matrix can share the same integers for the time being. I'm not going to pass this back to the user, this matrix, but I'm constructing a C matrix which is shallow. The P array is shallow if it's there at all. If it's null, then it's not shallow. The H array is shallow. The I array is, well, if it's empty, nothing happens. The integer array is just C of I is just A of I. And it's also shallow, and it's of the same size. And the shallow will be true. Well, unless it doesn't have such an array. In very special cases, if you're applying identity, this whole code takes constant time because the values are shallow too. So that's short circuit. It's I call pure. If you see the burble, it says pure shallow. You just got order one apply. It's a pure shallow. Then, now that I have this matrix C set up, I have to fill its numerical values that are different. And I call apply op to do that, which is the same thing as I just called here, but I didn't have to create that shallow matrix to do it. So on the right, this apply op is being done in place on the output, the user's output C matrix, because it's just C equals F of C. Here, I've had to allocate X new space. So it's out of place apply. For this, in this case, it's for this, I'm calling it for this C is this temporary matrix over here. So it's fairly elaborate actually, what I've done so far. Even it's just a simple thing called apply. Well, why am I doing all this work? Well, I want to save time, right? I mean, if you want to take A equals absolute value of A, for instance, C equals abs of C, I want to say replace all the negative number, with their absolute value. Well, why make a memory copy? I want to do this in place. So I need to handle that. I need to have I need a way of doing that and capturing that information. Yeah, I also need to handle the ISO cases carefully. Like, do I need to, are you applying an operator in such a way that the output value will be non-ISO, but the input value is ISO? Whoops, that can happen. Like, what if you have a matrix that's all ones? Say it's an int64 matrix and all the values are 1. And you apply a unary operator that replaces all the entries with their row index or their column index. It's not ISO now. It was ISO before, now it isn't. So this will expand that if it needs to. Okay, which is going to be a weird case. But I have to blow up the main, you have one place to put the numbers. I now need a million places to put all the values of the C matrix. So I have to expand from convert an ISO matrix to a non-ISO matrix. I have to expand the values before I can apply them, do the apply. So that's what I do here. But so GB apply op is the workhorse for doing this. Now here it's out of place, and here it's in place. And in GB apply op is agnostic whether it's in or out of place. You just give it input matrix and the output array where its values go. I do need to still the matrix on input because you may have a matrix, an operator that's positional. It depends on the position. So I can't just have a pile of numerical values that I apply an operator. If it's just a unary operator, yes, that's all I need. A plain unary op, unless it's one of my crazy index ones. Or if it's an index unary operator, then I need its positions. So I have to pass in the entire matrix here. And the same thing for this. So that's what GB apply to op does. So I apply the operator. So CX is just op of CX done. Actually, op of C is probably better because it's going to work on the indices as well. Here, C of X equals op of A, not of itself C. And then we're done. We applied the shallow op, or we applied directly the apply op. And so now we have our temporary matrix. So before I dive into apply op, well, maybe I should dive into apply op right now. So this is where the meat of the algorithm is happening. GB apply op. And so where is GB apply op happening? It's going to be happening in several places. You've seen it used now in two places, apply op and shallow op. And there's the header definition. And it's also, let's see, I guess it's in the top level GB apply function. I forget what I do it there for. Let's see. It's also possible that I've converted an MXM into an apply. There's some MXMs which I can detect you're multiplying by a diagonal matrix I've detected. And I look at that case and I realize, oh, this is the same thing as a GRB apply. Let me just call a GRB apply and do it that way instead. And the transpose might just do an apply because it may want to do an apply and then transpose. Or actually, I think what it's doing instead here for these cases, it's decided that, oh, you're doing a double transpose. Oh, that's an apply. So things, all these methods map to other methods back and forth all over the place. So let's look at GB apply op. This is where I'm going to now do all these different kinds of applies. Okay, so this is the workhorse method. We've already seen all these other methods. We've seen the top level methods, the user callable. They call GB apply, which does error checking. And I think that's this method here, isn't it? Yeah, this is GB. Whoops, I've modified it. How have I modified it? Oh, I haven't. Okay, good. But now I want to call GB apply op. This is the one that's going to actually implement the algorithm. And so now what it's doing, start off with assertions. I want to declare a small array, which, what's the size of this? It is it will be allocated. It's going to be an allocated space. Who creates it? Let's see. Oh, that's by this beast, which is hiding up a whole bunch of terms. It's a macro that's going to, I maybe went a little bit too crazy on my macros. Okay, so this is declaring a pointer to integer that will be use later on in that works. It's in the workspace. So this is now finally going to figure out which algorithm to work to do the data on. Okay, so I first thing I do is some more operator renames. I change positional binary operators, which I'll have to change this because there's only a certain number of these. I'll have to change this when the index unary comes into play. But these are, if it's one of my current existing binary ops that are positional, I'm just applying them in a unary sense. So now I can simplify them. First of I, well, that's just position I. And so I replace some of the operators. Again, let's see. Okay. I figure out some number of threads to use. I figure out whether or not, does the operator depend on the column index? If so, I have to be careful about how I divvy up the work to the thread. So this is the slice matrix method. So now I'm starting to get ready for the slice. Yeah, slice, the slice folder. Okay. This is a shorthand for something that happens all over the place. So I just stuck it in a macro. Slice matrix. I need to take this input matrix and I want to create a set of tasks for the OpenMP parallelism down below. And since it's an apply, it's a very lightweight operation. The load balancing it turns out it's useful to create 32 tasks per thread that I have. So if I have 8 threads, say if I have 10 threads, I'll create 320 tasks. I'll cut the matrix up into 320 pieces. And I do that by calling my EK slice methods. Okay, so what I do here, and these are this slicing is not the way we slice the matrix up for the GPU. GPU can't do this. So this method has to be potentially called by a JIT. Some of the JIT kernels have to call this method. It's a very widely used method. So I use a macro for the prototype because it's a callback method that the JIT kernels must have access to from the libgraphblas.so. So it's a prototype that's going to appear inside the JIT kernels as well. And so I just made a macro for the prototype, which is commented out here. This is the prototype of the method. Because I need to do a type def of it as a function pointer as well. And so what this is going to do is it's going to return an array, a descriptor of all these tasks. And the size of the descriptor, I have to create 3 integers per task. So if it's 320 tasks, I have an array of size, 960. And so what this method is going to do is it's going to look at this matrix, and it's going to construct tasks, and each of these tasks have 3 integers in them. It has which is your first. So here's this large matrix A, imagine it's stored by column. What the slice methods do is they say, here's a slice of a matrix. Now the slicing, and I should pull up my other camera, but my machine died, so I can't do that yet. Oh, HyperSparse, by the way, is dead, unfortunately. Did I tell you that? The cooling system died.
Is that the
DBX
GPU
workstation.
system?
The
Oh,
GPU
yeah.
system, yeah, and it's end of life, so they won't repair it.
Is it liquid cooled?
Liquid cooled, yeah. I don't know if I'm just going to toss it or whatever. So
Oh,
I'll
you could
fly
probably
my desktop.
aftermarket repair if the cooling system bad. You could probably get an aftermarket liquid cooling system. Yeah.
I might look into that. I don't know yet what I'm going to do. Okay, so if I matrix store by column, this piece here is a slice. And I do this in a funny way because I might be cutting into the middle, like the first vector. Whoop, that doesn't make any sense. I drew this wrong. So this might be a slice of a matrix in hashed. Okay. So the first vector is k first. The last vector is k last. The task always owns some of this first vector, but it may not own the first part. So this is p start. There's three integers that decide to define this task. The first vector it works on, the position it starts on, which is somewhere in that first vector, and then it stops at the p start of the task after it, of the next task, which is right here. So I know where to start, I know where to finish, and I do everything in between. That's my goal. But I may have to start in the middle of the first vector. And when I finish the last vector, I may have to stop early because somebody else is doing this piece down here. And the reason I did this rather funny slicing of a matrix is because what if I just working on a vector of a billion entries? I've got 8 threads, just chop, 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 right? Well, that's a special case of this, where the k first is equal to k last. What if you've got a power law matrix and you've got a celebrity, you've got a vector that's got a billion entries and the rest of it's got 5? You may want to give one thread the first half of the matrix, another thread the last half of the matrix, and let all the threads work on that middle column with the billion entries. Again, that's a generalization. That's a very specific case. This is the general format. This will handle all those different cases. So the slice method is going to produce tasks that look like this, a bunch of them. And then every task is described with those 3 integers. And so that's what these 3 arrays are doing. And how I do that, I mean, okay, it's very simple. The first thing I do is I create all the positions, P, I just divide it up uniformly. And then I figure out for each of those tasks. Now this is not parallel. Every task, then I figure out, well, what vector are you in position P? Find yourself. And so it's a search, it's a binary search. But there's only 320, say. If I have 10 threads, I may decide not to create any tasks at all. I mean, the number of tasks I create might be just 1, in which case it's and number of tasks 32. Let's see. Hang on. Oh, well, this passed the macro. Um, uh, so this sets up my parallelism. And unfortunately, I probably, this is kind of overkill. I I don't actually need to do this if I'm going to call CUDA. I do it anyway, which is silly. I should stop and not do that. But the CUDA kernel you see down here is very new. Vidith just worked on this, the CUDA case. Um, I should not do this slicing unless I know I'm going to use the CPU, because I'm not going to pass the slicing to the CUDA kernel. It's going to do its own slicing.
Yeah, I assume
So
it's
now,
gonna take warps into
yeah,
consideration.
yeah,
But yeah,
it'll divide it up in its own strategies. And basically, this slicing here on CUDA, all this work is done by every thread block itself with its own binary search if need be. And binary search is different, and it's a very different beast. So this is not done on the GPU here anyway. This is just for OpenMP parallelism. So now I go through like 1, 2, 3, 4, 5 different cases. Let's look at those 5. So there's 5 different kinds of apply. Really, I could have put these into 5 different functions. It might have made more sense to break these up that way. So it's a little more, and then I'm done. So they're totally 5 completely independent branches now where I'm going to go. And like I said, it's kind of a big file. It's what, 800 lines. I could have broken up into functions because they're totally non-overlapping. The first thing is the positional case. And here, since and the index unary op doesn't trigger this case, or the user defined, I should say, index unary op. This is only if the operator is a built-in positional operator, in which case this is a mistake. I tend to not do this. He's got a line here that's blank, but it's got blanks in it. I don't do those because it's harder to navigate with Vim because it jumps across it. Do you see left and right bracket? Curly bracket jumps across that space. Anyway, so I usually don't
yeah,
do that. So Vidith edited this code. And I also don't put curly brackets after parentheses like this. I would do this instead. That's not my style. I'm very stylistic. Okay, so he has several branches. So these 5 different cases, totally 5 different algorithms. So it's going to be 5 different CUDA kernels as well. And here, it's a unary apply of an operator. I guess it's positional, and he just calls. I guess he calls it 3 places, the same case. So he folds my cases together, which is fine. Probably not the right way to do it, but it works. So we call the CUDA kernel and says, nah, I've refused to do it, or it doesn't exist, or we don't have CUDA. And if a method refuses, it returns no value. So now we've decided, oh, we have to do a positional op on the CPU, and it's positional, so there's only certain numbers of these. It's either position I, which is one of my built-in ones, or row index is a similar operator. And here it's like a built-in template. It's not a factory template. I'm not calling out to the factory kernels. I'm doing the algorithm right here with this being the definition of what it means to apply the operator. And this is doing the algorithm apply, because the algorithm is so simple. but let's look at it. This does not depend on J. So let's look at apply template. This is calling GB apply, pulling in the code for unop IP. It's just a simple loop, parallel loop. But the apply operator is give me the row index and stick it in the output matrix. Now apply J is different. It's give me the J, which is not part, which is now totally it's the IJP. It's GB apply unop IJP algorithm. It's this one, which now it's going to depend on the slicing of the matrix. We've called this only this array only is constructed up above here by this slice matrix method macro. Okay. And so this thing, J is a column index. K is the kth column, because it's all stored by column. All the matrices are pretending to store by column. If it's a CSR matrix, I've just done this, right? It's the same algorithm. I need to know the column index. And it's not part of the data structure. It's where you are in the matrix. So I can't just iterate all over the values of the matrix and just get the row index and use it. That's the IP method, where I have the row index. It's part of the data structure. Just grab it, apply it. I don't need to know what column I'm in. I just get the row index. And again, they're all stored by column at this point. But here I need the column index. So I have to iterate. I have to slice the matrix like this so I know what column I'm at. So now each task, and so this structure all the way to here is a parallel loop that is predicated on the fact that you slice that A matrix. So it's going to iterate across the tasks constructed by slice matrix. And then it's going to do some stuff on those vectors, but it has to iterate across. So I have to get the task. So I have a parallel loop, one, and I call them tasks, but they're really just, there's my parallel task loop. I have OMP, pragma OMP, parallel for num threads. I always have a num threads clause all the time, because I want every OpenMP loop or parallel construct to have the number of threads controlled, because I'm told how many threads to use. Schedule dynamic comma 1, which sounds like a really stupid way to schedule a parallel for loop. But this is a very small, short loop. It's 320 tasks. Every task is a large chunk of work. So my task is one iteration of that loop. So that's why I want a dynamic, because they're going to take potentially different amounts of time. Although maybe not, right? I could maybe do maybe I could have done a static schedule for these tasks. But typically I'll do a dynamic schedule because tasks are slightly irregular because I've got to figure out where I am. So I get my K first, there's my task, get the K first and get the K last, and then iterate over those vectors that I have to work upon. It might just be one, K first might equal K last. So the task has to iterate over those vectors. And so this is what it's going to do. But the first and the last, so I have to figure out now, oh, you're on the kth vector. Give me your name, kth vector, that's J. So I'm very careful with my use of letters I, J, and K. I is a row index, J is a column index, K is the kth vector of a matrix, let's say. Sometimes it's also just a generic for loop and iterate. If I'm iterating across, so this J equals AH of K thing, if you go to the, let's see, it's a built-in, no, built-in include GB matrix.h. Okay. If you look at this generic way of iterating across a matrix, this is a sequential iteration. It has this thing here, like give me the name of the kth column. Oh, well, it's sparse. J is equal to K. It's the same thing. Give me the name of the, oh, it's bitmap. Oh, it's the same thing. Oh, it's a dense matrix. Oh, J is equal to K. If it's hypersparse, you have to look it up. Okay, so that's what this is going to do. It's going to, if it's hypersparse, it'll do the lookup. If it's not hypersparse, it will, and somewhere at this point, I will have defined that macro. I forget where I do it. I think I do it. Where do I define that macro? Somewhere, I must, because I'm using that. Let's see. I probably do it in one of these up here. I can't recall. That's funny. Where do I do it? I don't remember. Okay, then I have to get the start and finish of this vector. So if it's the first one, it's this one and this one, right? The first and the end. I have to get, okay, I'm at the kth vector, and I have to iterate over that kth vector. And so this is a macro that hides a bunch of gnarliness that gets all that information. I just repeat this over and over again. So I just made it into a macro. I could have made it into a static inline function as well, but I just very short, simple things I make macros out of. And then I do the work. So the final work looks an awful lot like the simpler algorithm, template, GB apply, unop, IP. Is just iterate and apply the operator. But this operator has to have it's dependent. It's not a parameter to this macro, but it depends on J. And so I've got to know where I'm at before I can actually apply the operator. And that's where I'm at is what all of this is supposed to be doing. I iterate across the vectors so I can tell where I'm at. And then once I know where I'm at, I'm on the first, I might decide, oh, I'm on the first or the last column. If I'm in the middle column, where do I start at the kth, start of the kth vector, the end of the kth vector is these two arrays. And I get that this way. So I've actually, it's kind of funny, I forget where I define those. Sorry, it just took my phone away here. Okay, are you there?
Yep.
Okay. Yeah, I hate it when your phone rings, it steals your Bluetooth headphones.
Oh, right. Yeah.
And it was a spam call, no less.
All
All
and
right, so
just a time check. I know you're getting up
it's
on
6:20. Yeah,
6:20. Yeah.
we're almost to a good stopping point. We've almost walked through an entire algorithm in quite a bit of detail because there's a lot of things like the slicing of a matrix. The algorithm itself is super trivial, extremely trivial. Let me go back to look at. Let me finish this apply op method. So we've done so. So I've renamed the positional op. So I go through and I've got all the positional ops that are 64-bit. These are the 32-bit, in which case I have to do the typecast. Okay. Or I guess they're Boolean. The positional ops are either 32-bit, 64-bit, or Boolean. Like you can apply trill as a Boolean operator. Right? That's permitted. It's an index unary op. It's positional, and this is the operator. It's true or false. Why? I don't know. Well, there it is. And I just hard code it. This is kind of unusual. Usually what I'll do is this will be a switch case. And most of the algorithms, when I have a built-in method like this, it's what I call a factory method. And I'll have a switch case, which calls a kernel in the factory kernel, as I call it, which then will do the work specific to that data type into an operator. The factory kernels, though, can be disabled entirely. And so here, these can't be disabled. They just always do it, and they're always present because they're so simple. And rather than creating the other methods, and I just put them in a big switch case, and I actually do the code. The algorithm is right here, splat, right stuck into the method. So that's the positional operators. This takes constant time. Apply an ISO. I'm constructing one value. This is an order one apply of any kind of operator. If the output matrix is ISO valued, I construct its ISO value right there. Otherwise, now you see the factory switch cases. If it's a unary op, okay, again, I check, oh, you have CUDA? Great, do it. And this can now be disabled. Compact means if you compile with GB compact, it means that you're turning off the factory kernels, and these then can be turned off. And I also have a switch case. I have a hack in when I'm testing in MATLAB, I can turn them off at runtime as well. That's what this if is there for, but otherwise it's not active. So the factory kernels always look like the following framework. Okay, define the worker for the switch factory. If I grep for that, if I go up 2 levels, you're looking at a very stylized piece of code here. Define the worker for the switch factory. That comment is always the same. So you see it, you know you're going to dive into a big switch case called the factory, a switch factory, I call it. And then the first thing I do is define the macro, which is the switch case for that particular instance. So you see, I'm constructing a name of a function I'm going to call. That's a macro that's building a function name with these parameters. So let's look at one of these factories. It's the UNOT factory. So cd apply factory. So now I'm in the factory, and there's 2 factories. These are just big switch cases. GB UNOT factory is a factory which handles all the opcodes. And sorry, I do have a few cases where I go over 80 characters. It goes through all the opcodes. Here are the floating point opcodes. Like the inputs are code 1. Oh, these are absolute value from real to complex. I've got these opcodes, which are Boolean, floating point to Boolean. I've got other opcodes where the input output types are the same. Like here's all the z equals minus x methods. And you see this first 3 parameters, okay, I guess the first 3, GB worker, UNOP, Z name, A name. Oh no, it's these parameters here are defining the name of the method I'm going to call. So if you go to the factory folder, factory kernels, there's a whole ton of here. UOP, these are calling the UOP. You see here, I'm calling these this is a macro that's doing string concatenation, and it's going to call a method GB uop apply with these three strings tacked together. So uop apply. Let's see, uop apply. Yeah, well, it's the name of the file is just uop. So here's all the uop methods, and how many are there? There's a bunch, and they have three components to their names, like logical negation on floats. You can do that. That's a built-in operator. I don't know why they did that, but there it is. That's all these different unary operators. Then this is calling one of them. This is calling one of them. And if we look at one of them, like, I don't know, let's just look at the square root of, say, float. Now, there's actually there's two methods in this source file. This source file provides two methods. It provides the one I'm calling right now because it's a unary apply, but it can also do a transpose. This is going to do a transpose and take the square root of a float to produce a float matrix. And this is going to pull in the transpose methods, not the apply methods, but this is going to pull in the apply template. So I have additive inverse, multiplicative inverse, all the different built-in operators. They're all with a worker. Now, some of these workers may refuse to do the work. They may not be present. And that's this disable macro. So for example, this disable macro says, well, if you don't want square root in your set of factor kernels because you want to reduce the size of the binary, or if you don't want any floats, which is kind of silly, but whatever, then these operators are disabled. Otherwise, you get them. And this is an important one, so it's not going to be disabled by default. Square root of a float is going to be present in my by default, but you can turn them off. And so some of these may refuse to do the work, in which case you get no value, which is what happens when you refuse to do the work, you get no value. What if there's typecasting? Well, my operators don't do typecasting unless it's identity operator. Then I typecast. Then those are typecasting operators. And that's the case where I do typecasting in the factory kernels because you're doing apply to take a float typecast to double. That's the user's intentional, like that's the best thing they want. They want to just do a typecast. So I put in typecasting kernels to do that as built-ins, not as generics. Anyway, so the worker here is one of these switch cases. But other methods may define other workers, like transpose, for instance. That's going to be another instance of this factory. So here's all the built-in operators. No user-defined operators are going to come this way. The user-defined operators don't go this route. Now, if the switch case refuses to do it, why might it refuse? Well, it might be compiled with compact. So you don't have no factor kernels, or you have typecasting, or you call a worker that's been disabled because you didn't want to compile it because you're trying to save binary space. So, okay, it didn't happen. So let's JIT the thing. So we call the JIT instead, and we've seen how that works. What if the JIT refuses? Maybe the JIT says, hey, wait, this operator, there's no string. I can't compile it. You didn't give me the string. No value. Finally, we go generic. And the generic is, in this case, it's not a positional operator anymore because those are just the special built-in ones. It doesn't depend on it's a plain old unary operator, but it's a function pointer. And the input matrix may have to be typecasted to the input of the operator. So I have a function that I do have a factory, but this factory returns a function pointer which does a single typecast of a single scalar. And then I call it 1 billion times on each scalar. And I apply the operator. a billion times on each scalar. So it's crazy slow. It's the same algorithm. Apply UNOP IP. It's that same, where is it? In the kernels, in template. It's this same algorithm. It's just a very expensive set of functions. Now, over here, where is it? Over here, I apply the UNOP template, which is this thing. It's a more general purpose thing. This thing is, okay. All right, I guess I split this apart. Slightly different. I check this if it's bitmap, I don't have to test it, and if it's bitmap, I do this. So I made this slightly different. Okay, so that's the unary op. Binary op, similar sorts of thing. I extract the kind of method I need. If I need to typecast the scalar, because if it's a binary operator, it's bind first or bind second. I typecast the scalar if I need to into this workspace. There's the scalar. And then I do the bind first or the bind second. There's a CUDA branch and there's a factory. But this is a different factory. It's no longer the unary op factory, it's the binary op factory. And I have a binary worker, a binary op worker. But I'm going to call the bind first method. So here, say it's, I don't know, what is it called? What am I going to call it? I think it's EY. Is it EYs? Let's see. I think it's the EYs methods. Like, let's say it's times. And I think, let's see, is it going to call bind first? Yeah, there it is. So it's going to call this method. You're going to pass in a scalar, and then you'll pull in the bind first template instead. This method, where I grab the, now I can templatize across the type. So I get the type of the scalar. I get the type of the input B matrix, and I'm applying C of the output array CX is op of the scalar comma B matrix. So I have to iterate over the B matrix and apply a binary operator, not a unary operator. And so that's what this does. And the bind second is similar, it just is reversed. But again, I have whole other factory for that. So bind second looks very similar, it's down here. But it's just using a very slightly different template. And that could fail, right? That could refuse, or the bind first could fail. I have a bind first JIT, I have a bind second JIT. And then what if any of the binary ops fail? Okay. Then I use a generic. And here the generic, I could have put this generic test inside the bind first, bind second, but I didn't. But the generic, again, there's two cases for the generic, the same algorithm, except that here I go directly to the IP. I use the GB apply op macro, and I do all the binding in the preface up here, one at a time. Anyway, so I've yeah. Finally, we have a user-defined index unary op. See, all the built-in index unary ops have been accounted for because they're all positional. They're all handled up above, like row index and first I and second J's, things like that. Now we're down to the last case, which is the index user-defined index unary op, again, I have the CUDA case. If that fails, I do the JIT, and if that fails, I do the generic. And the generics are always the ugliest things. Like, this is calling a function pointer that has to be given the row and the column indices, both. And I don't know if you're going to use them. Maybe you just want the thunk. You don't need the row indices or the column indices. I'll give them to you. Sorry. And they're not cheap to get. I have to call my more elaborate method. It would be nice to know, like if you define a user-defined index unary op, if you could somehow tell me, yeah, this is index unary op, and it depends upon, it potentially depends on four things: the input value to the matrix, the row index, the column index, and the thunk, the scalar. Well, you could tell me that maybe it doesn't depend on all those. Maybe it only depends on us. Maybe the operator only depends on a few of those things. Like if it doesn't depend on the J, then maybe I don't have to use this macro IJP, this IJP method, which has to, you do the slicing thing, and I give you the column index, and imagine it's stored by column, and I give you the column index, and you say I don't need it. Oh, I could have done this instead. I could have done a simpler method.
Well,
Or
something
just
we can
apply.
consider for 3.0.
Yeah, it's something to consider. Like you have these very, these operators are getting complex. Like a binary operator, the first operator is powerful because I know it does not depend on X, it only depends on Y. What if you wanted to create an operator that's a binary operator that's Y squared? You could tell me, don't bother to load X from memory. Think about that. Think of the memory traffic you just saved by doing that. You're not reading in one of the input matrices values. You're just reading in the second one. Wouldn't that be nice? Now, a clever compiler might be able to do that when it's jitted, because you'll load the value and then you don't use it. The compiler might be able to say, oh, don't bother loading it. It's clever. Are compilers that clever? Well, they should be, right? I don't know. Yeah, version 3 of GraphBLAS would be nice to have. It could be done with GRB set and get, maybe. You do a GRB set to tell this operator, hey, this operator I just defined, by the way, here's a hint, don't give me the input values to the matrix. It depends on just J and the thunk or something, or the theta, if you want to call it that, whatever. But it doesn't depend on I or whatever. Then I could use faster algorithms as a result. So because the unop JIT, if it's an index unary operator, I have to pull in my IJP kernel. So if I go to the JIT wrappers, there's 4 of them, but then I go to those are just the wrappers. I go to the JIT kernels. There's 3 of them. There's bind first, bind second, and apply a unary operator. And I think this is also the one I call for the index. Yeah, index unary op. And here I know, if I know at compile time, it depends on J, I have to use the more complex algorithm. Otherwise, I can use the simpler algorithm. Problem is, if it's a user-defined index unary op, that's true, because it just depends on J, because I don't know. So anyway, there you go.
Cool.
That's GRB
Yeah.
apply.
Yeah.
One last thing really quick, and we'll stop here. I'll just say one thing really quick. And I won't dive into this algorithm, it's complicated. But there's one last step. Once I constructed this T matrix, it may or may not be shallow. It may have lots of shallow components, some are shallow components. I finish off the work here with the accum mass phase. This may take order 1 time. If all the stars align, there's no accumulator, there's no mask, and T just is T and C is empty, then C is T. I just slap the data in and I'm done. Otherwise, it does some work.
Yeah, it seems like that applies to most of the algorithms, so we'll probably have to go over that
Yes,
at some
they
point.
do.
Yeah.
Yeah, yeah, we will. And the next thing we'll do is, I think, is a Q mask, actually.
Okay.
Although what it's going to call is the EY's add in some cases. So all these algorithms are coupled to each other. Like you've already touched upon the transpose. We haven't looked at the transpose yet. You know, these algorithms are, if you look at who calls what, it's a rat's nest because they're all gluing together like Legos, right? That's what linear algebra looks like. So act-lgb accum mask, you're going to see it in lots of places. Apply, reduce, MXM, Kronecker, transpose, they both add and multiply, assign, extract, select, everywhere. At the end of all these primary methods, there's an accum mask phase. So, all right.
Yeah.
Good
Well,
stuff, my
thanks a
friend.
lot. Stop the recording.
Yeah, you've seen kind of the over